In this video, we're going to look at IP version 4 addressing. I'm going to give you an overview of IP version 4 addresses and explain the basics of IP version 4 addressing. From now on, I'm going to refer to IP addresses, but be aware, please, that I'm discussing IP version 4 addresses in this video and not IP version 6 addresses. We're going to look at an overview of IP addresses, what they look like and how they function. I'm going to explain the various address classes that you get in IP version 4. In other words, Class A, Class B, Class C, Class D, and Class E. We'll also talk about CIDR or CIDR and how that changes the address classes. But as a foundation, it's important that you understand the 5 address classes A, B, C, D, and E. We'll look at special IP addresses, including the loopback address, the local broadcast address, and other special addresses. And lastly, I'm going to explain what network masks do and why they're important with regards to IP addressing. So what is an IP address? An IP address is a layer 3 logical address assigned by an administrator. Unlike MAC addresses, which are hard-coded or burnt into network interface cards by the manufacturer, an IP address is configured by an administrator. The IP address may change within a subnet. For example, when using DHCP or Dynamic Host Configuration Protocol, an IP address resides at a layer 3 in the OSI model. Please refer to the OSI videos for more details on how the OSI model works. An IP address is used to uniquely identify a device on the network and is used by routers to determine where that device is. So a router routes traffic to a destination IP address based on a hierarchy of network and host, which we'll talk about in a moment. So once again, the IP address uniquely identifies a device in a network in a similar way to how houses are uniquely identified in a street. Houses in a street have a unique address. So for example, 10 Oxford Street. In the same way, a host in a network has a unique identifier on that network, being its IP address. I'm going to expand on that analogy in the next few minutes. Every device on the internet has a unique IP address. So there are millions of IP addresses out there, and no two devices can have the same IP address for communication on the internet. Every device needs a unique IP address, and hence the move to IP version 6 these days because of IP version 4 address exhaustion. So for example, you cannot have a device 10.1.1.1 communicating with another device with the same IP address. That's going to cause a conflict in the network. Every device on the internet has its own unique IP address and requires a unique IP address for communication. Now, I will be talking about RFC 1918 addresses in a moment. In that RFC, private IP addresses are explained. So 10.1.1.1 is an example of a private IP address as specified in RFC 1918. In a lot of organizations today, private IP addresses are used internally, and then those addresses are NATed or network address translated onto the internet. So when a device with IP address 10.1.1.1 is NATed to a public IP address, such as 12.1.1.1, the public IP address, in this case 12.1.1.1, needs to be unique on the internet. For now, just understand that IP addresses on the internet need to be unique from each other. Network address translation, or NAT, once again, is not covered in this video, but I will be discussing NAT in this set of CCNA videos. So be aware that in the real world, multiple companies may use IP address 10.1.1.1, but those addresses are NATed to unique IP addresses when those devices send traffic onto the internet. Now here's a quick demonstration of some IP addresses. If I ping www.yahoo.com, notice that the domain name is translated to an IP address. So in this case, yahoo.com is translated by a protocol called DNS, or Domain Name Service, to an IP address of 87.248.112.181. DNS is used to convert easy-to-read names two IP addresses. It's much easier to remember a simple name such as yahoo.com or cisco.com or bbc.co.uk rather than having to remember the IP address of those domain names. As an analogy, this is similar to a phone book where we are translating human-friendly computer names to IP addresses. But what I'd like you to notice is that the IP address of yahoo.com was resolved and we got an IP address of 87.248.112.181. I could ping another website such as hp.com. Notice the IP address is translated to 15.192.45.139. Now, a lot of websites don't permit pings, which uses ICMP, so the request times out. But notice that the DNS server did resolve hp.com to a 15 address. Now, in a moment, I'm going to explain what Class A addresses are, but for this example, HP own the 15 Class A public address range. So anything that starts with 15 in the first octet belongs to HP. Here's another example. I'll ping google.com. Notice in this case it resolves to 74.125.233.50.